So Olivier Courtin, I'm working in GIS field since years, and I founded Data Ping company. One of our main focus is to build bridge between GIS fields and deep learning stuff. So how are we able to extract insights from geospatial data through the latest available tool that we have? We already knew how to do it with spatial analysis in a classical way, but what can we extend with new tools to go further? That's it. And so this presentation is about a computer vision tool able to extract information from imagery. That's it. That was my 1 minute presentation. So the framework is called net.io.ping. And if we go back to the history, everything began with a loop. So it's a Wiener loop 1 century ago. And the point is to say that you have to understand what is wrong before to be able to fix it. And you loop again and again. But since you are not able to understand what is wrong, there's nothing to do about. So if we look about authorization nowadays, it's widely used. There is a vast amount of information available, but we are unable to use it really. And most of the pixels acquired, we don't do anything with them. It's a waste. So the idea, the need, is to say, okay, we are able to gather pixels, but what can we do with this pixel to be able to switch from pixel to insights? That's the key point. If we look about the deep learning stuff, supervised learning is quite simple. You have one input, one expected output, and you train a neural network till it's able to compute the output from the input. And the key point is the loss function. The loss function is the ability to compute the distance between what he performed and what it expected. Since you are able to compute a meaningful distance function, you are then able to find a way to converge to a solution. Okay? So since you train a model rightly, you're able only with the input to use your trained model to compute an output. That's it. Okay? So it's only a way to train a model. So what is really a trained model? There are several ways to understand it. We will focus only on one because it's the simplest one to understand. It's a compression. You only compress your information, the whole imagery information, and you accept to lose a lot of information, but you keep all the information you need to achieve your task. So it's just a directed compression stuff to lose the information, but the one you have to keep for the classification. So once you understand it, net.io.ping is just a way to build a bridge between geospatial data and deep learning stuff. There is a three tasks we are focused on. First is quality analysis. So once you train your data and you are able to compute an output, you will be able also to compare this output to an alternate data set, and so to put in evidence if there is a significant difference, yes or no. And for instance here, in pink, it's what is predicted by the model. Yep. In pink, it's what is predicted by the model. In green, it's the labels, and in the gray is when both are gray. So it's a quick way to be able to check if the model and the label are matching, yes or no, and to see that this one, for instance, it's because it's behind the trees. So it's harder for the model to find a building because it's hidden. And it's also interesting to see that if you zoom out, there is Spotify differences which will help you to save time because we will focus only on the part where there is enough differences between your two data sets. One other thing you can perform with exactly the same framework is change detection, because in this scenario, you will train a model and use an alternate input. For example, something like 1 year later, or 2 years later, or 1 week later, any time. And you will so compute an alternate output and compare the difference. Okay? And the last one is feature extraction. You will train your model with a small dataset train area, and you will use a wider imagery input to compute output. For instance, you will only label a small area, and once your model is trained, you will be able to launch the prediction on a wide area and thereafter to vectorize it. So to be able to use the tree scenario, we have several little tools you can assemble with kind of Lego stuff. So there are small tools, and you can change them to create your own workflow. So it's a command line interfaces. And the whole idea is the ability to deal with different kind of imagery, different kind of well-known labels format, to compute the prediction, and thereafter to do something meaningful with as insights from the prediction mask you generated. Okay, so that's the key concept. About the stacks, we reuse some well-known computer software from GIS field. Some came from Python imagery, and some came from deep learning world. So it's a bridge between these worlds. It's full open source except the NVIDIA parts, because it's not open source by NVIDIA itself. It's easy to deploy. It's not because we use a lot of software that we didn't package. So it's just a single line to install the whole stuff. There is a 101 tutorial who help you to do it by yourself, and so to learn by yourself by doing it with real world data, and something from the install to the data preparation, training, and so on. Take something like 2-3 hours to launch the whole training session and the whole results. So it's also available online. So if you want to look at it right now, you just have to click on it, and you click on the different picture to zoom in the leaflet interfaces. So all you need, in fact, is imagery, and we've seen that it's not a problem anymore, GPU, and you need at least a recent GPU with enough memory, and labels. And so the key point is the label, because most of the time we have labels, but not accurate enough. So if you look here on OSM buildings data, we have buildings from this imagery. It's true, but they are not accurate enough to be sure that your trained model, if you use this kind of data, will be really accurate. So it's something important to keep in mind, that if you are garbage in label, you will have garbage out prediction. Yeah. So the point here is also to reuse this technique to check that your dataset training is quality enough. And so to compare your labels you use here with these really tools, and so also be able to keep or not some labels, because, for instance, here these buildings appear in the label, but it's not right related to this imagery, because it's right now on this imagery there is no buildings at this time. So the most common way is to remove these ones, and there is an integrated tool to help you to keep yes or no in a second. So what's new inside an ETO.ping? First is the ability to enhance the quality of the prediction despite the fact that we use tiles. So it's well known, we use meta tiles to enlarge the focus. Obviously, it will take longer if we choose this option, but the result here is cleaner, okay? So if we slow the whole process, we have to improve it some other way. So we add the multi-GPU scaling to help to use as many GPU you can get on a single host and for the trend and the prediction. So you can scale it up. And also we add the multi-classes. So you are not only obliged to use it on a single class, you can use on several classes at once. And we also provide an auto-weighted unbalanced option will help you to give weights related to the classes if they are not distributed in the same way in your dataset. So what's the limit right now? First, the kind of imagery you want to predict on must be quite related to the ones you already train on. Remember, it's a kind of compression. So you can't expect a good result if the kind of imagery has nothing related to the ones you use for the training. About the labels, we've seen that you need something accurate. And the amount of label you need is something like thousands. So at the very least 1,000 or few thousands, it depends, but not a dozen, okay? And also, right now, it don't deal with topology. So if you have something you want to extract and it's topology related, something like a network, so roads, for instance, it doesn't work well. It's far better behave with surfaces, any kind of surfaces, okay? Right now, we are still working hard on it, and we are looking for funding, for sponsor in any way. It could be related to code, so pull requests are really welcome. It could be related to money funding. It could be related to hardware funding, and so on. So help us to increase again accuracy, especially on low resolution. We talked just before about Copernicus and Sentinel. The next step, obviously, will be to behave and to increase the resolution even before we perform training and prediction on it. The topology, obviously, and to reduce the amount of labels we need before be able to have an accurate training, and also go on the performance improvement, because it's not necessary anymore to have a huge infrastructure to be able to use it. You can, but it's not mandatory. There is also alternative open source to this project. There is Raster Vision, EOLearn, RoboSat, Solaris. So why choosing this one? Few arguments. We really focus on G-standard compliancy. So it's really easy and standard compliant to reuse all the geospatial format data you work daily with. Your data preparation will be easy and fast. There is a built-in web UI interface which helps you to check at every step that everything is online, yes or no. It's modular and extensible, so it's not something you can't extend easily. On the contrary, you can really easily add new tools, add new interfaces, add new templates, and so on. It's also handle multi-bands imagery and also handle data fusion. So you can, for instance, use vector, rasterize your vector, and add an input from your imagery. So it's really the same kind that a GIS map. You compose your map by adding several layers, and with this stack, you can train and then compute. It's high performances and it's accurate because we use and reuse the latest computer vision papers available. If this field interests you, there is in one slide all the best resources to learn from it. Yeah, one slide about the company. To take away, there is right now industrial open source AI4 framework available. The performance are already okay to use it at a country level. You not need anymore to be a computer vision scientist to use it. A geospatial guy who understands the idea of the compression can do it right now. Plain open data could be used to train a model because you can use it step by step, and so to refine your labels till they are accurate enough. And funding and pull requests are really welcome. That's it.
Okay, thank you. For once, we have more than 1 minute time for questions, so bring it on. Yes, please.
How does this compare to RoboSat?
It was it's just a rename.
Could you
Yeah.
repeat the question
Yeah.
a bit louder, please?
I asked, there's another framework called RoboSat Pink,
Yeah.
which is similar.
Yeah, RoboSat Pink was the name of the previous version.
Okay.
Nitio.pink is a rename, is a 0.7 version of the 0.6 RoboSat Big version. The point is there is a RoboSat project and RoboSat Pink. And a lot of people made the mistake. And when I told RoboSat Pink, a lot of people understand the RoboSat. And so at the end, it was a mess. So I said, okay, we stop it. We rename it. So it's Nitio. There is no Nitio anywhere. So it's a new name and go on. So it's the 0.6 version. Yep.
Do you have statistical output about how well the model performs? Does it give you any statistics on your training?
Related to these ones? No. Right now, no one at my. I don't have any information that anyone compare this whole framework. It will be a really good idea on several aspects related to accuracy, related to performances, and related to how easy it is to use them. Yep, it's a need, in fact. But at my, I don't know anyone who did it before. Yep.
The example of the computer vision in the right is basically
Yep.
use Python. So
Yep.
I suppose it is like a unit. So it's
Mhm. Yeah, it's a unit like with an encoder, and you reuse an encoder as a ResNet-like. So you can choose any kind of ResNet as an encoder. It's a unit-like, and there is also a copy from the encoder to the decoder as a unit, but also on the decoder part.
This makes much easier to just getting started because it's a bigger utilities and framework.
Yep. Yep. Because yeah, you already have all the PyTorch and argumentation. Argumentation is data augmentation. Yeah, data augmentation and data augmentation able to deal with multi-channel, and data augmentation able to deal with several kind of imagery color shifting. So you can add a lot of noise in your model, and because you add a lot of noise, the model is forced to generalize enough to be able to still work even if the imagery in the input will slightly change.
It's some big augmentation.
Yep.
Okay. Anybody? No? Then once again, thank you very much.
Thanks.